Okay, this is the video lecture for Thursday, September 10th for Math 283. And the topic today is the dot product. So let me just motivate this. When we talked about vectors, we mentioned that you could multiply a scalar times a vector. And the effect that had was it maintained the same direction as the vector, as the previous vector, but it multiplied the length by the factor c. But then that brings us to a question: can we multiply two vectors together? And the answer is we can. There's actually two ways to do that, and the dot product is one of them. So let me talk about what is meant by the dot product. Well, let's suppose we have two vectors, A, which is given by A1, A2, and A3, and another vector, B, given by B1, B2, and B3. The dot product of these two vectors is written like this. So A, and then you place a dot, and B. And it's defined as A1 times B1 plus A2 times B2 plus A3 times B3. So to get the dot product, we just multiply together the respective components of the two vectors, and we add this together. Now, something to note here, this is a number. So this is a scalar. The result of the dot product is a scalar. It's not a vector. And that will differ from the curl, which we'll talk about tomorrow. Let me do an example problem with this. So let's say we have two vectors, A equals 2i hat minus 5j hat plus 3k hat, and B equals minus I hat plus 3j hat plus 2k hat. So here are our two vectors. Let's calculate the dot product of these two vectors. The dot product we get by multiplying together the respective components. So we have 2 times minus 1 plus minus 5 times 3 plus 3 times 2, and this will give us minus 2 minus 15 plus 6. And so that comes out to minus 11. So the dot product of these two vectors in this example is minus 11. The dot product has there's some properties listed in the book for the dot product. I'm not going to go over those. The dot product is distributive and it's commutative. One important property I will mention, though, is if you take the dot product of a vector with itself, you actually get the magnitude of that vector squared. Okay, so this is an important property to note. And this is actually quite easy to prove, but I won't prove it right here in the interest of time. Okay, let me talk about an important theorem in regards to the dot product. And this theorem has the following form. It says the dot product of A times B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So this is a second way to calculate the dot product between two vectors. The dot product between two vectors is equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And I'm not going to prove this, although I will set up the proof. And we may do the proof in class. If you have two vectors, A, and another vector, B, and this vector right here is the vector A minus B. And we can label this angle between these two vectors as theta. We can use the law of cosines here to prove this is true. And we'd write this like this. The law of cosine says A minus B squared. The magnitude of this vector is equal to the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A, I'm running out of room here, magnitude of B, cosine of theta between them. So this is how we would prove this theorem is true, but I'm not going to do the proof right here in the interest of time. But I do want to do an example problem. If you guys remember in the previous example, an example problem illustrating this theorem. In the previous example, we had these two vectors, A equals 2i hat minus 5j hat plus 3k hat, and we have the vector b equals minus I hat plus 3j hat plus 2k hat. We had these two vectors. We calculated the dot product. There's something I wanted to mention here first before I do this example, and it relates to why we would do this example. This theorem is very useful because we can manipulate it. We can use it to find the angle between two vectors. And we do that by solving this for the cosine of theta. So if you have two vectors, the angle between those two vectors is equal to the dot product of those two vectors divided by the magnitude of the first vector times the magnitude of the second vector. This gives us the angle between the two vectors. So the example problem I wanted to do here, and I just got a little ahead of myself, was to calculate the angle between these two vectors. We found earlier this dot product is minus 11, okay? But now I can use this formula, cosine of theta equals the dot product, which is minus 11, divided by the magnitude of each vector. Now let's calculate the magnitudes of each of these vectors. The magnitude of A will equal the square root of 4 plus 25 plus 9, where I'm squaring each component. And that will give me, 38, square root of 38. The magnitude of vector B is equal to the square root of 1 plus 9 plus 4, and that equals the square root of 14. So these are the magnitudes of my two vectors. And now I can put these in the denominator. So I get square root of 38 times square root of 14. Okay. And now to do this problem, this comes out to minus 11 over 23. I now would take the inverse cosine to get the angle. And if you do that, this angle comes out to 118 degrees. Okay. So this is the angle between these two vectors. So this is a very useful theorem to find the angle between any two vectors. I want to talk about the interpretation of this theorem, though, and the dot product in general. If you want to intuitively, or in words, qualitatively, the dot product is really a measure of the alignment of two vectors. When two vectors are very closely aligned, meaning they're close to being parallel, the dot product is positive and it's a larger number. If two vectors are perpendicular, what if two vectors are perpendicular? So let's suppose A and B are perpendicular. Well, if they're perpendicular, theta equals 90 degrees, and cosine of 90 equals 0. So if you have two perpendicular vectors, and this is an important property to note, the dot product is 0. Or in other words, if you take the dot product to two vectors and you get 0, you know those two vectors are perpendicular. And finally, if the dot product is negative, such as it was here, that means these two vectors are more anti-aligned. It means they're pointing in relative opposite directions. Okay, so it's important to know the interpretation of the dot product. Let me talk about one more topic I want to mention today is the projection of one vector onto another. Okay, so suppose I have two vectors, and one vector is a vector A, pointing like this. Another vector is a vector B, pointing like this. I might be interested in the projection of vector A onto vector B, okay? In other words, if I shined a light from above, what would the length of the shadow of vector A onto B be? Or in other words, how much A-ness is there in vector B? Okay, and that's called a projection. And we're going to determine some equations for these projections. There's two types of projections. There's a scalar projection, which is just basically the component of vector A onto B. And this is written as component of vector A with a subscript of B onto vector B. And this component is simply equal to the magnitude of A times the cosine of the angle between these two vectors. This is the component of vector A onto B. And I'm going to just kind of rearrange things to derive a formula, a slightly different way of writing this. So I can multiply by 1, but I'm going to multiply by the magnitude of B over B. And then I'm going to rearrange this, and we can write it as 1 over the magnitude of B times the magnitude of A times the magnitude of B times the cosine between those two vectors. And then I can, this is just the dot product by our previous theorem. So now I get the vector A dot product with the vector B over the magnitude of vector B. And this is the component of vector A onto vector B. Okay, that's the component of one vector onto another. So that's how much A vector can be found in the B vector. This is a scalar projection because this is just a number. We can also have a vector projection. Okay, with the vector projection, the way we write this is the projection of vector A onto vector B. And the vector projection is simply the scalar projection times a unit vector in the direction of B. And so I can write this as A dotted with B over the magnitude of B times the unit vector in the direction of B. Well, that unit vector, we talked about this before, it's just equal to vector B divided by the magnitude of vector B. And now if I simplify this, what I get is the dot product of A and B divided by the magnitude squared of vector B, okay, times vector B. So this is now the vector projection of vector A onto vector B. By the way, this has applications in physics in particular. When you find the work is the projection of the force vector onto the direction of motion, or often called D. And so this is one, finding the work, you would use the scalar projection of the force onto the distance vector. So that's one application I can think of. Let me do an example problem with this. Let's go back to our two previous vectors. A equals 2I hat minus 5j hat plus 3k hat. And vector B equals minus I hat plus 3j hat plus 2k hat. We found the dot product of these two vectors is minus 11. And then we also found the magnitude of B here to be square root of 14. Okay. So now for these two given vectors from our previous example problems, let's find the scalar and vector projections of vector A onto B. Well, the scalar projection would be the dot product, which is minus 11, divided by the magnitude of B, which is square root of 14. And that's it, basically. So this is the projection of A onto B. And if we calculate a number here, what does this come out to? This comes out to minus 2.9. Okay, which actually indicates the angle between these vectors is greater than 90 degrees. The projection, so the vector projection of vector A onto vector B is equal to the dot product, which is minus 11, divided by the magnitude squared, so that'll be 14, times vector B, okay, times minus I hat plus 3j hat plus 2k hat. And what we can do here is multiply this out. And if we do that, we get 11 fourteenths times I hat minus 33 fourteenths times j hat minus 22 fourteenths, which reduced is 11 sevenths times k hat. So this is the vector projection of vector A onto B. And again, this has some important applications in the physical sciences. Okay, I'm going to stop the video lecture there. There's one more topic I want to cover, and that's direction angles, but I feel like this video has gone on long enough. So in class tomorrow, I'm going to discuss direction angles with you guys the first part of the class. That won't take too long. I might do a proof of the theorem I mentioned, that the dot product is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, and then we'll work some practice problems together. So I will see you guys tomorrow.